Let's start this video by discussing the important points of Witting reaction. First of all, Witting reaction is the most important and perhaps the easiest way to produce alkenes. So, we can form alkenes. This is a single step reaction and it is topic of further research. And what is this fourth point is the most important, that we can control the final product. That means either we can obtain this geometry or other we can obtain this geometry. This one is called Z, this one is called E, as we can see in lot of examples. Here we are obtaining Z, here we are obtaining E, and here E is formed. Same, here we are forming this as major product. So, Witting reaction is quite important reaction in organic chemistry. So, let us now move on to the mechanism of the Witting reaction. In a Witting reaction, the aldehyde or ketone is treated with a phosphorus based compound which is called phosphorus aldehyde. It results in formation of a four-membered ring which contains oxygen as well as phosphorus. This ring is called oxaphosphatine ring. Since this is an intermediate, it dissociates to give the final product, in which the carbonyl bond, this C double bond O, has been replaced by C double bond C. So, alkene is formed at the end. As for the mechanism, it is quite simple. The ketone, the carbonyl group, is attacked by the negatively charged carbon atom of the phosphorus aldehyde, which in turn results in the formation of intermediate. This intermediate, as we know, further dissociates into the final product. Now, next question arises, how aldehyde are formed? So, the answer to this question is quite simple. Aldehyde can be formed by starting from triphenylphosphine, and let us say we have started with methyl bromide. In this case, a SN2 reaction takes place which results in the formation of this product. Now, due to the presence of positively charged phosphorus, the acidity of these protons which are attached to the carbon increases. Acidity of hydrogens is increased. As it is increased, they can be easily removed. So, therefore, a phosphorus aldehyde is formed. Let us take another example. Cyclopentyl bromide, when treated with triphenylphosphine, undergoes an SN2 like process to give you the phosphonium compound in which phosphorus is positively charged, and now the acidity of this hydrogen is significantly increased. Now this hydrogen can be removed by a base to give you the phosphonium ylide, negative on this carbon, and phosphorus is positive. Once again, this is happening, the acidity is increased due to the presence of P positive, phosphorus positive. Now, in the next step, the ylide formed can be treated with any aldehyde or ketone in a manner which is similar. Let's take an example with the help of, let's say we are treating this with acetone. So what will happen? This negative charge will attack the carbonyl carbon. The electrons will go to phosphorus. So this is a concerted process, you can say, concerted process which is occurring in a single step. Due to this, once again a four-membered intermediate has been formed which contains phosphorus, oxygen, carbon on both sides, alright. So this oxaphosphatine breaks down to form the final alkene product. And also triphenylphosphine oxide is formed. So this is all about the mechanism of the Witting reaction. Okay, now let's discuss the selectivity in Witting reaction. So if you look at both these reactions, in the first reaction a Z alkene is formed, whereas in the second reaction E alkene is formed as the product. This selectivity in case of Witting reaction can be easily explained if we look at the structure of both the ylides. If you can see both these ylides, these are different in structure. So what happens due to this structure difference? If we let's name it as Y1 and this one as Y2. In case of Y1, let's draw PPH3 positive, and yes, now this ylide is formed from Y1, whereas in case of Y2 we will get after the treatment with base this negative, this ylide. Now this ylide, this negative charge can delocalize over the neighboring carbonyl group. As a result, the negative charge is delocalized over to oxygen. Therefore, Due to delocalization, this is stabilized. But Y1 is not stabilized by any such delocalization. So, elites can be, depending upon this phenomena, elites can be classified as stabilized elites, which is the one used in second reaction, as in case of first, elites are oftenly termed as unstabilized elites. So you can easily form a relation that whenever an unstabilized elide has been used, it will result in the formation of Z alkene. Whenever a stabilized elide is formed, E alkene is going to be the final product and it is going to be the only product. So now next question arises, how how the stability of elide determines stereochemistry, determines the stereochemistry of final product. So why is stabilized is forming E alkene and non unstabilized is forming Z alkene? The answer is the answer is that whenever a unstabilized elide adds to the aldehyde, the formation of oxaphosphatine is irreversible and it is always kinetically controlled. As a result, this both these molecules they are added to obtain the least repulsive intermediate. Now once this intermediate is formed, this breaks in a stereospecific manner. That means only one product is possible, that is Z alkene. Therefore, unstabilized elites always form Z alkene in the Witting reaction. On the other hand, whenever a stabilized elide is used, like the one we have used in second example, now the second step, that is oxaphosphatine formation, is now reversible. It is no longer irreversible, rather it is reversible. That means both isomers can be formed like this. Now this is CO2R, this is R. So this is the syn isomer and this is the you can say anti-isomer. Therefore, the syn isomer can go back here and go back here into the anti-isomer. Now they are in an equilibrium. This will result in formation of Z alkene, which is sterically less favored, whereas now this anti-isomer, which is more stable, it will always form E alkene as your major product. Although this is debatable but this is the explanation most scientists agree. So this is more, you can say, it is thermodynamic control once the eyelid is stabilized. Again we are repeating it. In case of unstabilized eyelids, the formation is irreversible and kinetically controlled. As a result, syn oxaphosphatine is formed, which in an irreversible manner forms Z alkene, whereas when the eyelid is stabilized, it gets time to establish an equilibrium between syn and anti diastereomers of the oxaphosphatine intermediate, and the anti diastereomer under thermodynamic control forms E alkene as the major product. I hope you like it. Thank you very much.